Watch raw energy attempt to move through an unstructured environment. It searches for a path, strikes a boundary, and violently disperses. Standard network theory attempts to solve this chaos with a simple rule. If a topological edge exists between two nodes, it implies a guaranteed capacity for transfer. An edge represents a connection. This diagram exposes a specific failure in that logic. We have two identical network graphs. On graph 1, a signal pulse injected at source A reaches node B cleanly. On graph 2, the exact same pulse injected down the exact same topological path diffuses into nothingness halfway across the gap. A purely topological map lacks the vocabulary to explain this failure. It registers the line, but ignores the gap's physics. These failures suggest that topological consistency is not a predictor of signal success. To understand why one path survives while the other collapses, we have to measure the behavior of flux within a physical medium. Chapter 7 of the Unified Harmonic Systems Framework provides a diagnostic lens for this topological illusion. Within this framework, transfer is a constrained flux struggling to maintain integrity against the dissipation of an active, noisy medium. Survival is dictated by admissibility, a set of local criteria that a signal must satisfy at every point along its journey. To dissect a network failure, we apply three specific UHS constraints: the carrier modulation split, boundary damping, and coherence corridors. Designing systems based solely on topological maps without applying these admissibility constraints creates brittle networks that collapse under real-world noise. We begin the diagnosis by narrowing our focus from the macro network down to the mechanics of a single isolated edge. Transfer relies on a carrier, the baseline energetic medium that physically persists across the bridge. This diagram distinguishes energy from information. A smooth, low-frequency wave forms the carrier. Wrapped around it is a complex, high-frequency pattern, the modulation. Crossing a defined medium interface completely erases this high-frequency pattern. The medium acts as a filter, scraping off structural modulation. Standard theory assumes that partial signal degradation still allows for partial comprehension at the destination point. In UHS, the loss of modulation means the structured transfer has vanished into the noise floor. Verifying a pathway for carrier survival is mathematically useless if the system relies on structured modulation to transmit actual state changes. Boundary loss is a product of physical turbulence. A smooth, concentrated beam hits a textured interface and immediately splinters into chaotic noise. Expanding our analysis to a three-node sequential path allows us to evaluate how these interfaces behave in sequence. It is an analytical error to average local edge metrics in an attempt to calculate an overall network conductivity. When a signal hits an abrupt change in admissibility conditions at a node boundary, local edge quality is no longer the dominant factor. The signal is immediately subjected to three specific interface failure mechanics: reflection, leakage, and mode mismatch. Observe this three-node pathway to see coherence destroyed systematically. At the first interface, mismatch introduces slight phase distortion. At the second, partial reflection occurs. Approaching the third node, the signal completely fragments into static. This compounding loss, medium-composed damping, pushes signals below the noise floor. Investing in high-capacity individual nodes is futile if the interfaces connecting them harbor unresolved admissibility mismatches. Zooming back out to the macro network level, we evaluate how global architectural choices dictate transport survivability. UHS defines three operational classes of transfer. Diffusive transfer spreads across many paths. Ballistic-like transfer preserves directional concentration, while wave-like transfer relies on phase recurrence. Testing two architectures under identical load, a centralized hub on the left and a distributed motif network on the right, a sudden noise spike strikes both simultaneously. The hub architecture immediately shatters into slow diffusion, while the distributed network successfully protects local ballistic transport. This reveals a category error, conflating entangled bridge correlation with actual causal signal transfer. The mathematical proof that correlation does not equal transfer is the Anderson localization limit. Watch the nodes glowing simultaneously. They are perfectly correlated. However, the directional flow lines between them drop to absolute zero. They cannot support actual causal flux between them. Optimizing a network for maximum topological connectivity without isolating true causal capacity generates a false map of systemic resilience. We can now return to the connectivity paradox that opened our analysis. Applying our UHS diagnostic lenses to the failed graph, structural flaws emerge. Red markers flag interface boundary mismatches. A measured coherence limit line expires before reaching the target node. The topological edge existed, but the signal's coherence was completely consumed by medium composed damping. This diagnostic outcome demonstrates why theoretical models require stress tests through active perturbation sweeps to identify where hidden regimes begin to collapse. A network pathway is only validated if it survives both carrier and modulation checks while under active perturbation. A system that has achieved sustainable looping looks like this: a continuous band cycling through a closed circuit without losing intensity. The requirements for UHS transfer are clear: validated interface consistency, protected coherence corridors, and verified causal flux. These rules are the foundational prerequisites for achieving higher-order system stability. Once bounded transfer is secured, these robust pathways allow local reactions to link together reliably. Mastering the mechanics of bounded transfer is the mandatory step before we can explore how closed transfer loops eventually generate systemic memory and complex structure in Module 8.